Hello and welcome to 1.6 Relative Motion. In this lesson we're talking about movement relative to some frame of reference, some other reference point. And that reference point might be moving as well, so we're going to take a look at how this all combines. So to start with, we need to talk about frames of reference. A frame of reference is a coordinate system from which we measure motion. So really any motion we measure needs to be from some frame of reference. Now when we talk about relative velocity, this is velocity relative to some frame of reference. And the way we do this is that we can actually say that we can measure one movement relative to another frame, even if that frame is moving. So the way the math looks is we can say the velocity of A relative to C. So this is the velocity of A, so some object A, relative to C, where C is our reference point, or our reference frame. So we can say that the velocity of A relative to C is equal to the velocity of A relative to B, let's say B is some other reference point, plus the velocity of B relative to C. So you can see that I can sort of swap reference frames here. I can say that velocity relative to C, well, it's the same as the velocity of A relative to B and the velocity of B relative to C. So if B is moving as well, you can see how they sort of combine that way. And basically the idea is you can see we have A, B, and then B, C. You can see that the result is we get A, C. And I'll show you an example of even more relative here. We can say the velocity of A relative to F, this is equal to the velocity of A relative to B, plus the velocity of B relative to C, plus the velocity of C relative to D. You can see that I can just keep on combining these things, and as long as I can make this chain where I have A to B, B to C, C to D, D to, let's say D to E here now, and as long as I end up on the right letter, you can see that my chain sort of extends all the way along. We have A to B, B to C, C to D, D to E, and E to F finally. So the idea here is that we can combine a whole bunch of different reference frames this way. So it might make a lot more sense if we actually just look at an example. So let's look at this first example here. It says that passengers on a cruise ship are playing shuffleboard. The shuffleboard's disk's velocity, so shuffleboard is this sport over here where we push a disk along a surface. We try to get it into some goal. So the shuffleboard disk's velocity relative to the ship is 4.2 meters per second forward, and the ship is traveling in the same direction as the disk at 4.6 kilometers per hour, relative to Earth, when the water is stationary. So see, we have relative to Earth, and we have relative to the ship. So we're going to need to find now the disk's velocity relative to Earth. Okay. So the way we do this is we can say we want to find the velocity of the disk relative to Earth. So you see that I'm just using the letters D and E for disk and Earth. Well, this is going to equal the velocity of the disk relative to the ship, which we have, plus the velocity of the ship relative to the Earth. And we can just combine them this way. So you see that I get D to S and S to E. It combines this way. So now we write down the information we have. We have velocity of the disk relative to the ship. It's 4.2 meters per second forward. And I have the velocity of the ship relative to the Earth. Well, this is equal to, we had 4.6 kilometers per hour forward. But we need to fix this a bit because we have meters per second for the disk, so we're going to convert this to meters per second. So I can multiply by, there's 1,000 meters in a kilometer, there's 3,600 seconds in an hour, and so then I get 1.28 meters per second in the forward direction. Okay, and so now we can finally find the velocity of the disk relative to Earth. It's disk relative to the ship, so 4.2, plus the ship relative to the Earth, 1.28. And this gives me 5.5 meters per second forward. Okay. So, that's just an example of doing this relative velocity. We'll do another one. What is the disk's velocity relative to the Earth? So the same question. When the disk is now moving in the opposite direction. So now the disk is moving opposite. It's moving backwards. So now we can say that velocity of disk relative to the ship, we could say it's 4.2 meters per second backwards, or we could say negative 4.2 meters per second forwards. So that's all that's changed here, is our disk is now moving in the opposite direction. But the equation stays the same. Disk relative to Earth, disk relative to Earth is equal to disk relative to the ship plus the ship relative to Earth. And this gives us now negative 4.2 plus 1.28, which gives us 2.9 meters per second. You notice that our answer is negative 2.9, so I'm making it positive, and I'm just saying that this is going to be in the backwards direction. There's our final answer. Okay, one more here. What is the disk's velocity relative to Earth when the water is moving at 1.1 meters per second forward and the disk is again moving forward? So now we have another thing here. We have water moving. Originally we were saying the water wasn't moving at all. But now what we have, this changes things a bit. So the velocity of the disk relative to the ship is what it started out as. So it's going to be now 4.2 meters per second forward. Good. But now instead of having the velocity of the ship relative to the Earth, we only have the velocity of the ship relative to the water. And we know that the ship relative to water is moving 1.28 meters per second forward. And we have this added piece now that the velocity of the water relative to Earth is equal to 1.1 meters per second forward. So now we have three pieces. Still the velocity of the disk relative to Earth. Well, we always start with, if we're looking for the disk, we have the disk here. So this is how we build this. And it's a fairly sort of, it's almost just mathematic the way we can just put these together. We say we have the velocity of the disk relative to, well, we have velocity of disk relative to ship. So that's what I'm going to start with. And then so I have ds. Now I need to get from s to something. So I have s relative to the water. Okay. I'm still not at the Earth. So I need to keep going. I have the velocity of the water relative to Earth. And then I'm done. You see, so that can get our velocity of the disk relative to Earth. And now I can put in my numbers. I've got 4.2 plus 1.28 plus 1.1. This gives me 6.6 meters per second forward. And there we go. That's our final answer. On the next page, we're looking at, this is a kind of problem called a river crossing problem. So the idea is we have a boat heading due north as it crosses a wide river. The velocity of the boat is 10 kilometers per hour relative to the water. So this is the velocity of the boat relative to the water. And the river has a uniform velocity of 5 kilometers east. That's the water relative to Earth. And part A, we say determine the boat's velocity relative to an observer on the riverbank. So I'm over here on the riverbank. I'm on the Earth. So I'm trying to find the velocity of the boat relative to Earth. You see that we always just frame, for these questions, we frame our velocity for whatever reference frame we're using. So we have the velocity of the boat relative to water, velocity of the water relative to Earth. Now we want to get the velocity of the boat relative to Earth. Okay, so to solve this problem, we're going to say that the velocity of the boat relative to Earth, this is equal to boat relative to water plus the velocity of the water relative to Earth. Okay, and then we can just add these together. We have 10.0 kilometers per hour north plus 5.00 kilometers per hour east. Okay, so if I was to draw that picture, we've got north, east. I want to get the result. So there's going to be some angle, and I know that I'm going to be using Pythagoras. So I can get the magnitude here. This is going to be the square root of 10 squared plus 5 squared. This equals 11.18 kilometers per hour. And then my angle is going to be tan inverse of 5 over 10. This gives me 26.6 degrees, which tells me finally that the velocity of the boat relative to Earth is equal to 11.2 kilometers per hour north, 26.6 degrees east. And there's my final answer. Okay. So looking at part B here, it says, the driver of the boat now wants to arrive across the water at a location that is due north of his present location. He moves at the same speed of 10 kilometers per hour relative to the water, and the river is flowing east at 5 kilometers per hour, just like it was before. In which direction should he head, and what is the speed of the boat relative to the shore? So if I was to draw this problem, now the boat driver says, I want my total velocity, my velocity of the boat relative to Earth, to be pointing straight north. But to do that, well, we know that the velocity of the water relative to Earth is heading east, 5 kilometers per hour. And the question is, if I'm heading in this direction, velocity of the boat relative to the water, well, that's the direction I'm going to need to head in so that my total velocity here is going to be straight north. So the question is, if this is 10 and this is 5, what is this equal to? And at what angle does the boat driver need to aim? So we can start with the angle. We have, we're trying to find theta. We know that sine of theta, well, this is always equal to just the opposite over the hypotenuse. So we have the velocity of water relative to Earth was our opposite. Velocity of the boat relative to the water is our hypotenuse. And I have my values here. This is 5 over 10, or 1/2. So that means that theta is the sine inverse of 1/2, which is 30 degrees. Okay, so that gives us our angle. And it says, so what direction? So our direction is north 30 degrees west. And I guess that can be 30.0 degrees west. Good. Now the next part is how fast they need to go. So again, using Pythagoras, we have the hypotenuse squared is equal to the first side squared plus the second side squared. if I want to find velocity of b relative to e, it's the square root of this. And then I can fill in my values. I have 10 squared minus 5 squared. This gives me root 75, which is equal to 8.66 kilometers per hour. So we can say, therefore, relative speed is 8.66. Actually, yep, we've got 2 digits, so 8.66 kilometers per hour. And there we go. Okay, so there's one last page here talking about airplanes. Again, this is relative motion. And it's the same idea. We look at it the same way. So velocity of a plane, we could look at the velocity of the plane relative to Earth. And that's going to be the velocity of the plane relative to air plus the velocity of the air relative to the Earth. And these all have names. So we have the velocity of the plane relative to air. This is called the airspeed velocity. Airspeed velocity. Now that's a bit confusing because it's the velocity of the plane. The term airspeed just means the plane relative to the air. So it's not the speed of the air. Airspeed velocity is still the speed of the plane. Okay, and velocity of air relative to Earth, well, that is, that term is the wind velocity. So we have those two terms there. Now, there's 3 terms here: tailwind, headwind, and crosswind. A tailwind means that the wind blows with the plane. So it's going to be positive. It's in the same direction as the plane. Whereas a headwind is where the wind blows against the plane. And so if the wind's blowing against the plane, that means it's negative. It's in the opposite direction as the plane. And a crosswind is where the wind blows perpendicular to the plane. Perpendicular. Like this. So it's coming in from the side. Okay, and so there's one last problem here, which is looking at the air velocity of a plane. It says the air velocity of a small plane is 230 kilometers per hour north 35 east, when the wind is blowing at 75 kilometers per hour west 25 south. Determine the velocity of the plane relative to the ground. I'm going to help you start this one, but then I'm going to leave the end of the problem for you to look at. So we want the velocity of the plane relative to the ground. So like this, VPE. And we know that that equals the plane relative to the air plus the air relative to the Earth. Okay, and we can fill in some values here. We have VPA. So this is the speed of the plane, 230 kilometers per hour north 35 degrees east. And the velocity of the air relative to Earth, this is equal to 75 kilometers per hour west 25 degrees south. Okay, now you need to add those together, and it's just like any of these other problems, but unfortunately now this is a 2-dimensional problem. You need to set up your crosshairs. We can say that plane relative to air, north 35 degrees east, we're going up this direction. We have 35 degrees, which means this here is going to be 55 degrees. And you can drop your component. And then we have the air relative to Earth, 75 kilometers west 25 south. something like this. This is 25 degrees, and this is 75 kilometers per hour. So we have 75, 230. You need to break it up into the components. So remember, we have Vx is equal to, and then we have our components here. So we have 230 cosine 55 degrees. That's in the positive direction. Then minus 75 cosine 25 degrees. And you'll get the result there. We can get the y velocity is going to be 230 sine 55 degrees. That's positive. And again, the other one is going downwards, so we have minus 75 sine 25 degrees. You can get your answer, and then you know that you'll need to draw your triangle with the x and y. Get theta, get the result, and the final answer that you should get here is the velocity of the plane relative to Earth is equal to 170 kilometers per hour east, 68 degrees north. Okay, so see if you get to the same result, and I'll see you in the next lesson.